SwayamPrabha. Digital India. Educated India.
I am Dr. Rajiv Mishra, working as professor in the Department of Computer Science and Engineering at Indian Institute of Technology, Patna. The title of this lecture is Reinforcement Learning for Resource Allocation in Public and Private Edge Cloud Systems. Preface. In this lecture, we will cover the resource allocation in public and private edge cloud systems, and that uses the concept of reinforcement learning. So, especially we will discuss the resource allocation problem formulation for public and private edge cloud system using Markov decision process. Then we will consider this as two different problem. One is called parameterized DQN based resource allocation for public cloud edge system. Then we will discuss another formulation of the problem called deep deterministic policy gradient, that is DDPG algorithm for resource allocation problem for private edge cloud system. So, what we are going to see is that why there is a need of different deep reinforcement learning model different for public cloud edge system, and why there is another different required for deep deterministic policy gradient based deep reinforcement learning for private edge cloud. So, we are going to see all the details here. Now, let us summarize this particular slide before we go ahead. Now, it says that if let us say you have either there are two types of cloud, whether it is a public cloud or it is a private cloud. Now, in the edge cloud system, if let us say a public cloud is used, in a edge cloud system, if let us say a public cloud is used, then public cloud has different cost implication of different type of services. It has the different type of services. Public cloud will have different type of services, which is having a different cost implications. So, choosing not only between edge and cloud, but when you go for the public cloud, then which of these services are required to be chosen, this becomes a further optimization problem, and for that we will be seeing a different deep reinforcement learning, that is called parameterized deep reinforcement learning for modeling the public cloud and edge resource allocation. Similarly, if you are using a private cloud, then here we are having the decision whether to execute on the edge for lower latency. If the resources are not available fully by edge, then it has to be a private cloud. So, for that we are going to see another model which is a simpler model than PDQN, that is called deep deterministic policy gradient, and here we are going to only take the decision whether the resource allocation is to be done on an edge or a private cloud. So, all these things are the point of discussion. Therefore, to build the public and private edge cloud system, the resource allocation is going to be an important factor, and this is going to give the rise to the edge computing, and this is one of the most important concept which we are now discussing with the help of deep reinforcement learning, how we can do this kind of resource allocation in a public and private edge cloud system. Let us see the introduction. Now, the edge computing is proposed to provide the low latency and the real time services to the mobile users or any other applications. Now, edge computing provides a virtual pool of configurable computing resources, such as resource instances are often referred to as virtual machines. So, the resources which are to be allocated, we assume that it is to be allocated in the form of virtual machines, that is compute, storage and the network are packaged in the form of the virtual machines, and these virtual machines requires the virtualization of edge cloud, that is the virtualized edge cloud system we assume in place. So, in that virtualized edge cloud system, we are now seeing that the resources are allocated in the form of the virtual machines to the different to run different applications. So, the edge computing can provide the users with a low latency, location awareness and high quality service. However, these edge nodes usually do not exhibit the enough storage when processing the application, that is mobile data applications in the large numbers. Therefore, a collaborative edge cloud computing will provide the user with the computing services and requires the cloud and edge node to cooperate with each other. Now, in the collaborative cloud edge computing environment, the edge node with a limited resources can run more resources from the cloud node and pay that corresponding cost to meet the user's demand. So, here we are going to assume this kind of model, that if let us say that edge requires more resources, it can lease from the cloud node, but at a cost, and that cost is to be added with the user's cost. Now, because the computing cost of the edge node changes dynamically according to the workload, if no strategic resource allocation exists when the collaborative cloud edge computing provides this particular service, the computing resources in the edge node with a relatively low computing cost cannot be used reasonably, and computing cost will increase in that case. So, therefore, reducing the long term cost on premise of meeting the dynamic computing demands of the user is the key problem in collaborative cloud edge computing. Now, here the goal is to achieve the lowest operational cost under different strength of demanding amounts and computing time duration. So, in the edge cloud system, a node with a limited local resources can run more resources from the cloud node, and according to the nature of the cloud service, the cloud service can be divided into the private cloud and the public cloud. Now, in a private cloud environment, the edge node must allocate the resources between the cloud node and the edge nodes, whereas in public cloud environment, the public cloud service providers offer various pricing models for users different computing demands, and the edge node also must select the appropriate pricing mode of the cloud service in the public cloud scenarios, wherever, which is nothing but a sequential decision problem. Now, the decision problem is modeled using parameterized action Markov decision process, that is parameterized action Markov decision process in PDQN, and solved using PDQN and DDPG. Now, this can effectively reduce the long term operating cost of collaborative cloud side computing in various user setting. Let us summarize this discussion. Now, we see that there are two types of cloud, one is called one is called public cloud, the other is called private cloud. And we say that cloud edge, we say here also cloud edge. Now, when the edge requires more resources or additional resources, then it has to depend upon the public cloud services. So, it has to select which type of service it needs in public cloud, and this is called sequential decision problem. And the sequential decision problem requires a different model, and that is called parameterized action Markov decision process. This is to be modeled as parameterized action Markov decision process, that is PMDP, and this can be solved with the help of a specialized deep reinforcement model called PDQ, parameterized deep Q network, and this is what we are going to see. Whereas, in the private cloud, when the edge requires more resources, then it will now select from the private cloud, and this particular aspect, that is discrete, whether it is to be done from the edge or from the private cloud. So, this problem can be modeled as Markov decision process, and this can be solved with the help of DDPG, that is called deep deterministic. So, this is called one of the. So, this is what we are going to see here in the collaborative cloud side, cloud and edge computing under different. So, let us understand it more details. So, let us introduce you about the collaborative edge cloud computing. So, in the real environment, the cloud service can be divided into the public cloud and the private cloud according to their characteristics. So, private cloud, when the users computing demand randomly reaches the edge node here, for example, users demand when it reaches to the edge node, the edge node decide how to reasonably allocate the resources between the cloud and edge need to satisfy. So, if let us say that this edge node can satisfy all the requirements of the users, then it will not go for the private cloud, it will allocate all the resources. If it is not met, then the edge will then ask remaining of the resources between the edge node will ask for the additional requirement from the private cloud, and this is called the resource allocation from the edge plus from the cloud to meet the user's requirement. Whereas, in the public cloud, if let us say that edge node is connected to the public cloud, then in that case the cloud service provider now is offering, for example, Microsoft, Amazon, Google, they are all public cloud example, and they are offering different type of services, and these different services have various pricing modes to offer these cloud services. So, the edge node not only select the public cloud, but which service is needed, because all these services are having a different cost implications. So, the edge node also need to select the appropriate pricing mode of the cloud service for collaborative computing according to the user's requirement. Therefore, it is important to analyze how to allocate the resources efficiently to reduce the long term operational cost in the cloud edge computing system to satisfy the dynamic demands of the user under different cloud services. So, let us see about the private cloud scenario. In a private cloud environment, the edge node exhibits its own virtual machines to process the user's demand. However, because the number of virtual machines requested by the user may exceed the edge node's capacity. So, edge node needs to rent the virtual machines from the cloud node to scale up its capacity, that we have already seen. So, whatever is not met by the edge node, then edge node will request from the cloud, and here the cloud is the private cloud, and both edge node resources plus the cloud resources, the additional resources, both are required for the resource allocation of the user's application. However, the cost of private cloud changes dynamically according to the physical computing cost. So, the edge node need to dynamically allocate the resources at each time slot according to its resource allocation policy. So, therefore, it is not static, but it has to be decided for each time slot. So, the time is divided into the slots in this case. So, after the edge node allocates the resources through its policy, the computing cost of the edge node and the private cloud in this time slot can be calculated and then transferred to the next time slot to receive the new computing task. Now, let us see about the public cloud scenario. In a public cloud, when the cloud services of the public cloud, you need to pay according to the pricing mode. So, cloud service providers such as Amazon, Microsoft, they provide 3 different pricing modes, each of which exhibits a different cost structure. They are called on demand, spot and reserved instances. So, on demand instances, this pricing mode allows the user to pay a fixed time granularity set by the platform, and the price is fixed in a long period of time, that is called on demand. So, on demand requires no commitment, so cost the most but offers uninterrupted kind of service, whereas reserved instance this. So, reserved instance, this pricing mode requires the user to submit the reservation time in advance and pay the corresponding reservation fees to have the instances within that contract period of time. So, it is applicable to the user with a large number of computing demands, and the unit price is usually approximately 50% lower than on demand instances. So, spot instances are the third in this category. The instances of this mode is obtained by bidding, and the prices changes in the different time slots, which is usually based on the short term computing demand. So, this is the highest in the price segment, this comes a little less, and this even comes lesser than all these things. So, therefore, the price varies whether if you go for on demand instances will be quite more, reserved instances will be less than on demand, spot will be even required. So, let us see about modeling this particular system. So, assume that the each time slot t the user submits a demand for the resources, that is in the form of virtual machine. So, the user's demand for a particular time t can be represented as follows. So, that is user's demand at time t for demand for the resources are as follows: dt by L t. So, dt represents the number of virtual machines requested and number of VMs requested at time t, and LT represents the duration of service request, that is total time slots. So, the total computing resources owned by the edge, let us say that node is represented by capital E. So, as the resources allocated to the users, ET represents the number of remaining VMs of the edge node in time t slot. So, this is important, ET represents the number of remaining VMs of the edge node in time slot t. And the total computing owned by the edge node. So, the number of VMs provided by the edge node is expressed as dt. So, dt will be that demand minus and the number of VMs which is being provided by the cloud. So, demand minus which is being provided is nothing but the total number of VMs which are provided by the edge node, that is dt or by the edge, and ET, that is the number of. So, ET represents the number of remaining VMs of the edge nodes in a time slot t. So, it should be noted that if edge node has no available resources, it will hand over all the arriving computing to the cloud for processing. Now, when the resource allocation can be successfully performed on the edge node, each demand processed by the edge node will generate the allocation record in this particular manner, where DE is the number of virtual machines provided by the edge nodes in the allocation request, and LT is the remaining compute time of this particular demand. So, this becomes allocation record. Now, when a new demand arrives and the resource allocation is complete, the allocation record will be generated and added to an allocation record list in this particular manner. So, the record list H is maintained to keep track of the completion of users demand. Now, after the users demands are fulfilled, the edge node need to release the corresponding virtual machines according to the record and delete the allocation record from the list H. So, the number of virtual machines that completed the task and are waiting to be released at the end of time slot is given by eta. So, this is nothing but summation of all DE that means demand which is met by the edge that is to be released. Now, because it is the time is now time slot for which the virtual machine is demanded, that is completed, that is left time is 0. So, the number of remaining virtual machines of the edge node at time t plus 1 slot is as follows. So, E t plus 1 is equal to E t minus d t of E plus eta t. Eta t is the release of that particular virtual machine from that edge. So, E t plus nu of t minus d t will remain the number of edge nodes, the remaining virtual machines at the time slot t plus 1. Note that in order to quickly respond to the user's computing demands, even no computing demand is found, the machine still exhibits a standby cost. Therefore, the cost of the nodes consists of the standby and the computation cost. So, standby cost of one virtual machine in the edge node is, let us say, P e, and the computing cost of one virtual machine, the edge node is let us say Pf. So, the total cost of the edge node at a time slot t can be computed here in this particular manner. This is the total cost. So, total cost of the edge nodes will be computed as follows. So, it is the standby cost E t of P e, the total standby cost, and the total computing cost is that E minus E t multiplied by P f, that is the computing cost of one virtual machine divided by total virtual machines which are being given here by the edge. So, total computing cost. Now, at time slot, the cost of the collaborative cloud edge in the public cloud environment includes the computation cost of the cloud nodes and the computation cost of the edge node, which is as follows. So, for a public cloud, cost will be as follows. So, that is the demand of the virtual machine from the cloud, that is dC by T, dC, then multiplied by the cost of on demand instances, that is P of public cloud, and then this is x 1. Similarly, the cost of customization of reserved instances, that is on demand instance, and if it is of the reserved instance, then this particular cost is different, that is x 2 multiplied by P upfront cost. And if it is the reserved instance, that is if it is reserved instance, then this particular cost will be quite different, and if it is a spot, then it will be different, and this particular thing is a cost of the edge. So, if it is the dt which is being allocated from 3 different type of services, whether it is on demand service or it is the reserved instance service or it is a spot instance service. Now, here these xi values is equal to 1 if that service is used, 0 if it is not. Now, let us see about the parameterized. After seeing the cost, let us see the parameterized action MDP formulation in case of public cloud. Resource allocation. So, in a parameterized action Markov decision process formulation, let us consider about the states. So, the states consist of the features such as resource available at the edge, user demands, and the cost of that particular VM. So, here this comprises of the state space for the public cloud scenarios. So, that is ST means that state, here the edge resources which are, that is the edge resources, that is the VMs which are being allocated by the edge, and the VM they are waiting to be released, and user demand is dt, and PC is the unit cost of virtual machines in the private cloud. Similarly, this particular state space for the public cloud services, ST will become ET, here the edge resources for the virtual machines, and this is the virtual machines waiting to be released, and dt is the user demand. Here in a public cloud scenarios, these two parameters will be quite different. PT means the unit cost of spot instances in the public cloud, and ZT is the remaining usage time of the reserved instances. Now, let us see the second part in parameterized action Markov decision process, that is called the actions. So, action denote the ratio of the virtual machines that will be provided by the edge and the cloud. So, the action space for the private cloud will be having two different parameters, xc, that is the virtual machines which are provided by the edge, and xk is the virtual machines which are provided by the private cloud. Now, if it is the public cloud scenario, then the action space will be a little different. Here XC is going to be the same, that is the virtual machines which are being provided by the edge node remains the same, whereas here the public cloud instance will have the parameterized instance, that is called K. So, K will become 3 different type of discrete actions, that is K1 is if it is on demand instance, when K is equal to 1 2, when K is equal to 2, when K is equal to 2 then it is a reserved instance, and when K is equal to 3 is called the spot instance, and the virtual machines will be provided by private cloud of any of these instances. So, this is called parameterized. That is the K is equal to 1 or K is equal to 2 or K is equal to 3, one of these parameters. And so, if it is K is equal to 1, that is on demand instance will be allocated for VM, and if it is K is equal to 2, then it is a reserved instance of virtual machine which is being allocated, and if let us say K is equal to 3, then the spot instance of a virtual machine which is being allocated. Now, coming to the next feature in that particular Markov decision process formulation, that is called the reward. So, reward is the negative of the cost, and cost we have already calculated. In this case, we minimize the cost matrix. In reinforcement learning, we maximize the reward and thereby introducing a negative sign make it equivalent to the cost minimization problem. So, here the reward at time t allocation, that is if we consider a private cloud, that is the cost of a private cloud minus of it, that is the cost of the resource allocation in the private cloud, that will become the reward. Similarly, the cost of the public cloud at time t for allocation, the negative will become the reward function. So, let us see through the example. Now, consider the resource allocation problem where the user submits the following demand in 3 consecutive time slots. So, let us say that time slot 1, 2 and 3. Now, the demand dt that is comes, that is let us say 30, and the time slot is let us say 2. So, at a time slot 2, now demand comes for 2 time slots, and that is 30. Similarly, for at time slot 2, the demand comes for 10, and for demand 3, the demand comes 20 of 2 instances of time. Now, we are here, you can see that dt represents the number of virtual machines requested, VMs requested, that is dt, and LT represents the duration of the service requests. So, assume the slot 1 is the starting slot such that no virtual machine has been allocated a priori. Assume that there are total 80 virtual machines present in the edge nodes. So, total present is 80 VMs in edge nodes. So, the given constraints that the standby cost of virtual machines at the node edge is 0.03, computing cost of virtual machines at the edge nodes is 0.2, computing cost of a private cloud is 3, unit cost of on demand instance of a public cloud is 3, and unit price of the reserved instance is 1.5. Then customization price of reserved instance is 800 and unit spot instance is 1. Now, resource allocation in the private cloud. Suppose we have the private cloud and a policy has been deployed to allocate virtual machines per user demand, which outputs the actions, the following actions at each time slot. So, that is policy action is 0.4, 0.7, 0.8 xt. So, xt is 0 or 1 represents the ratio of the virtual machines allocated from the private cloud and the total virtual machines requested by the client at the slot t. So, the remaining virtual machines 1 minus are allocated from the cloud, from the edge. So, here let us say 0.4 is allocated from the cloud, but from the edge if you calculate 1 minus 0.4 is 0.6 and 1 minus 0.7 is 0.3, 1 minus 0.8 is 0.2. Now, calculate the cost collaborative cloud side, that is the cost of a private cloud allocation at these 3 different time instances. Also find out the number of VMs that will be available at the edge at the beginning of the 4th time slot. So, here all that calculations we have done. Let us assume that total available virtual machines, the edge is 80 at time slot 1. Let us say the demand is D 1 L 1, that is 32, and the action is let us say x 1 k, that is 0.4. So, that means so that 0.4 will come from the cloud. So, the total number of virtual machines which are allocated from the cloud is 12. The number of virtual machines which are allocated from the edge will be that D 1 multiplied by D 1 minus D 1 C, that is total demand is let us say 30 and 12 will be met from the cloud. So, the remaining 18 will be met from the edge. Now, the remaining virtual machines at the edge node, that is E 1 minus D E 1, that is 80 minus 62 will be 62 is the remaining VMs at the edge. So, resources can be successfully allocated from edge nodes, hence the allocation record will be generated here in this case 18, 2 means 2 time slots, and the allocation record will be H 1 is equal to 18 2, updated allocation record will be 18, 1, and the number of VMs waiting to be released is new is equal to 0, and the number of virtual machines available in the next time slot, that is E 2 is equal to E 1 plus N 1, that is 62, because it requires 2 time slots. So, in the next time slot not be available. So, the cost at the edge node C 1 is equal to E 1 multiplied by P plus E minus E 1 P f, that is 62 multiplied by 0.03 plus 80 minus 62 multiplied by, that is 5.46, and the cost at the private cloud is 41.46. Whereas, if you see at time slot 2, that is demand is 10 for one slot and the action is 0.7. So, that means 7 virtual machines will come from cloud and the remaining 3, that is will come from the edge. So, the number of remaining virtual machines at the edge node, that is 62 minus 3, that is 59. So, the resources can be successfully allocated from the edge node, hence the allocation record will have this update. Updated allocation record will after one instance 18 0 and 3 0, that is number of virtual machines waiting to be released, that is 18 plus 3, that is 21 after the next slot. So, number of virtual machines available for the next time slot, that is E 3 will be E 2 plus N 2, that is 59 plus 21, that becomes 80 in the next time slot. So, the cost of the edge node is E 2 P E, that is E 2 means that allocation, that is 59, and the cost is 0.03 plus the remaining is E minus E 2, that is 80 minus 59 is having that idle cost, that is 0.2, that is 5.97. The cost at the private cloud is, the allocation is, let us say that 7 multiplied by 3 plus the cost of this particular edge is 5.97. So, total cost is 26.97, which is correct. Similarly, for the time slot T 3, the demand for 3 is 20 and 2 and the action is 0.8. So, 0.8, that means 16 virtual machines is allocated from the cloud and the remaining is 4, and the 4 will be now allocated from the edge. And this is the cloud. So, the remaining virtual machine at the cloud will be 80 minus 476 and the resources are successfully allocated. So, that resource allocation list will be like this and the number of virtual machines waiting to be released after N 3 is 0. Why? Because it needs 2 time slots. So, the number of virtual machines in the next time slot will be available as 76, which is nothing but the remaining at the point at the time slot 3. So, the cost at the edge node is 76 multiplied by 0.03 plus 80 minus 76, 80 is the total available, that is E is equal to 80. So, capital E is 80 minus E 3 is 70, that is the idle time and that is 0.03. So, 0.03 is added over here and the cloud cost is 16 multiplied by 3, that becomes 51.03. Now, let us see about the public cloud resource allocation. Public cloud resource allocation, if we see that we have replaced the private cloud with the public cloud setting and the new policy that outputs the following time slot. So, k is equal to 1, 0 and 2 and x t is equal to 0.4, 0.7, 0.1. So, here k t is equal to 0 means on demand, 1 is reserved instance, 2 is spot instance. So, here it is the on demand and here it is the reserved instance and here it is spot instances. Now, calculate the cost of this cloud side collaborative cloud side computing, that is for the public cloud in a given public setting at each of these 3 time slot. Assume that the same demand were met by the client, that no customization is performed on the reserved instance. So, at time slot T 1, the cost of the edge node will remain the same. So, the cost at the edge node from the previous example was 5.46. Now, let us see about the public cloud. So, public cloud cost is that total number of reserved instances only here in this particular slot. If you see, go back So, it will be only the reserved instances which will be needed. So, for the reserved instance and this particular cost from the edge, that is 5.46 that we have plugged in, and the number of instances is 12, and for this particular reserved instance the cost is 1.5. So, total will be this particular cost. So, consider the cost of the reserved instance only since at time slot 1 the resources are allocated from reserved instance 1. Similarly, for on demand instance, this particular cost is being considered. Similarly, for the spot instance, it will be having the different cost. Now, let us see the DDPG algorithm. The full form of DDPG is deep deterministic policy gradient, that is DDPG is a policy optimization method based on classical actor critic reinforcement learning algorithm. So, here there are two different networks. This is one network, this is another network. Two networks together is used here in deep deterministic policy gradient method of reinforcement learning. The first type of network is called the policy network. So, policy network generates the actions. So, this is called the actions. Generate the actions based on the policy and interacts with the environment, whereas the critic network, that is the value network, evaluates the actor's performance through the value function that guides the actor's next action, thus improving its convergence and performance. Now, DDPG deals with the continuous action spaces. The exploration is managed by Gaussian noise n to the actions produced by the actor, that is the policy network. So, here you can see that it is the Gaussian noise added to the continuous action space. So, it is only used for the continuous action space. So, therefore, between the edge and a simple private cloud, this particular model of a continuous action space is applicable. Whereas, if you see the edge and a public cloud, there this particular problem is discrete action spaces, there this particular method will not work. So, this particular method will work only here in the private cloud situation, and why? Because this is to be worked in the continuous action space. Now, here let us see the other part, that is called the critic network. The loss function is the following. So, this is a del of j omega, and here we are looking up the loss function as mean squared error, which is between the predicted q values and the target q values, which is shown over here. In this case, where the target q value is calculated as the following equation, where there is a current reward R j plus the discount factor on the q values, that is of this particular value, and then you have the estimate of the optimal future values is given over here. So, once the target q values is given, then the target q values and this particular predicted q values is to be, this is the target q values, and this is the predicted and this is the predicted Q values. So, target Q values minus predicted Q values, and that del is taken as a loss function for the critic network that we have calculated here in this particular equation. Whereas, the actor network, the loss function will be as follows: del of that actor network, what we are looking up is the Q value which is given by the critic network, written over here, and this is nothing but the policy gradient. So, the parameters omega of the actor target network and the parameter of the critic target network are updated using the soft update. So, here you can see that particular actor network, and theta is, you can see that the critic network. So, both are being calculated here in this particular manner. Now, let us see about the PDQN, which is used for the public cloud resource allocation. So, the basic idea of PDQN is as follows. Now, for each action A in the parametric action space, because xc plus xk is equal to 1, we consider k and xk in the action value, that is q s a is equal to q s k and x k. So, here that S is from the states and k is the discrete action space selected at time slot t, and x k is the parameter values corresponding to the value k. Now, similar to DQN, a deep neural network is used in PDQN to estimate the parameterized q value. Here, that means that the goal of PDQN is to find the corresponding parameters, that is the parameter of the critic network, where when omega, that is the parameter of the actor network, is fixed, and it can be written here in this particular form. So, the loss function of the value network is written in this particular way. In a similar manner, the loss function of the policy network can be written here in this following manner. So, let us see about the training steps. So, the input of the algorithm contains the information about the user request demand dt at a unit cost of the spot instance in a public, let us say at time t. The beginning of each iteration of the algorithm, the edge node first select obtain the state of the collaborative and then pass the state as the input to the neural network into the strategy network to obtain the parameters of each discrete action. So, after the network edge network gets this action, it will select the appropriate public cloud type on the discrete values and determine the number of public cloud instances. Then interaction with the environment occurs to get the next state reward termination flag, storing this round of experience to the replay pool. The DRL agent will sample from the experience replay pool and calculate the gradient values, and then it will update. So, after one round of iterative to ensure the convergence of the resource allocation policy, the training will be continued and the maximum number of training rounds will be there. Let us see the Google cluster workload trace data set, which is used here in this experimentation. So, Google cluster workload trace data set contains the workloads running on 8 Google Borg compute cluster for a month of May 2019. The trace describes every job submission, scheduling decision, resource usage data for the jobs that run on these particular cluster. It has enabled a wide range of research in this particular. The new trace allows the explore these changes, and this particular trace data set includes the CPU usage information, information about the allocation, and information about the master worker relations. Now, this particular trace, and here the event task is being mentioned, that it has the features like time is the job ID and task index within the job. So, let us see about the results for the private cloud scenario, which is quite simple. What we will see here is that experimental results of low intensity groups. What we see here is the quite interesting improvement here in this particular case, that the cost is quite minimal by applying these DDPG algorithm. So, here also for example, low intensity groups and medium intensity and high intensity, in all the cases you can see that the algorithm which we are now discussing with the help of DDPG for a private cloud scenario, giving a very low cost in comparison to the any other method. Now, let us see about the public cloud scenario. The results are here in a blue color, which is shown as PDQN method. So, PDQN method also brings the cost to a minimum level. Here you can see the cost is reduced to a minimum level in the resource allocation scheme, that means between that public private edge cloud system, this particular results are quite less. Conclusion: in this lecture we covered the formulation, that is a resource allocation problem in collaborative cloud edge computing under private and public clouds. So, we have also used the method called Markov decision process using parameterized DQN and deep deterministic policy gradient to solve the resource allocation problem in making that particular process. We have discussed the results and some of the Google cluster workload data set also we have discussed, which is used for this experimentation. So, in the next session or in the further series of this particular discussion, we will see that how this particular how this system will make it into a perfect edge computing system, which will be a peer or at par with the powers of cloud computing through the edge computing, yet it is going to save the time, that is called latency, achieving the latency and reducing the cost, that is cost minimization, latency minimization and energy minimization. Thank you.